Okay, so what do you guys want to go over today?
I'm still shaky on chapter 10 mostly. So same.
Chapter 10. Okay, so let's do, so I have one question that I cropped from one of the past final. I forgot which final. So you guys can see my screen, right?
Yeah.
Yeah. All right. So let's work on this problem. And then if you guys have more questions, I can just take it from you. And I will turn off my video because when I start writing, you won't see me anyway. All right. So let's go over this question. So here's a question that was given in one of the past final. And you had to answer part A, that's a Fourier series. And it specifically says it's a sine series. So you know how to extend this function. And then using part A, you're going to answer part B. So let's start. So let's do part A. So I would say you can sketch the function, but it's optional. You don't have to. Why don't we just sketch it? I think it's nice. So we have f of x equals to the constant function 1. So here's our xy plane. And on the interval 0 to pi, now if you realize this is the interval 0 to L, right? Half of the period. So what is L in this case?
Pi.
Pi. So you can easily identify that from the interval or from the picture if you want to use it that way. So from 0 to pi, we have the function 1. So let's suppose this is 1, and that's the constant function 1. That's only half of the period. We want to extend this as an odd function because we're looking for the sine series. So that should give you a hint. You want to extend it as an odd function. So if I want to extend it as an odd function, that means I have to rotate this 180 degree or reflect it about the origin. So that would give us this half right here. So it's going to be sitting at -1 from negative pi to 0. And then if you replicate this more periods to the left and to the right on the x-axis, you'll have more pictures, but let's see how that would look like. So if I copy and paste, so I would have a graph here, and then I would have a graph here. So that's another period. And then you can do the same thing on the left side. We have a graph here, and then we have a graph here. So hopefully you get the idea. 2 pi, this is 2 pi, and this is 3 pi. And what the Fourier series is going to do, it's going to create this nice wave going through this function. So it would do something like this. So it will make a smooth curve. So we didn't really talk about convergence of Fourier series, but you might see it in the future. If you ever take PDE, maybe you will, who knows. But this is what we're looking for. That's our Fourier sine series. Again, the picture, you don't have to draw it. It's just good to have an illustration, what's really happening in the background. All right, so let's start. So if you're doing an odd extension, which coefficient will go to 0?
The A's.
Right, all the A's, right? So A0 will go to 0. AN will also go to 0 because we're doing an odd extension. And how do I know that? It's because the question says compute the sine series. So that gives you a hint. Well, we just need to compute what is Bn, right? That's the question mark. So Bn, by definition, is equal to 1 over L integral from -L to L f of x times sine of n pi x over L dx. So we know L is pi, and because the function is odd, right, we extend it as an odd function, and sine itself is an odd function. So odd times odd gives you an even function, right? So we can double the integral, 2 over L, and then go from 0 to L. Does this make sense, guys?
Yes.
Yep, okay. So now let's plug in L and f of x. So we have the following. We have 2 over L. L is pi. integral from 0 to L, that's pi, f of x, well, f of x is just a constant function, 1 times sine of, and pi will cancel out L because L is pi, so it's just sine of x and x dx. So we're just simply integrating sine x, sine n of x. And if you integrate this, we have, so the integral of sine is negative cosine, right? So we have negative cosine of nx over n, and we're going to take it from 0 to pi. Now let's plug in the endpoints. So we have 2 over pi from before. So plug in the upper limit, you have negative cosine of n pi over n minus, so that's double minus, plus cosine of 0, that's going to be 1. So we have 1 over n. Okay? And then you should remember cosine of n pi is what? What's cosine of n pi, guys?
Negative 1 to the n.
Right, so that we simplified it before, so we can use that here. So if I plug that in, I have 2 over pi, and I'm also going to pull out 1 over n. So that will give me, and then replace cosine n pi with negative 1 to the n. So we have 1 minus negative 1 to the n. And then you can simplify this more, right? So if what happens if you let n be even or odd? So we can break this up a little bit more. So if n is even, what happens? If n is even, we have positive 1, right? So you have 1 minus 1, that's going to give you 0. So all the coefficients are going to be 0. And when n is odd, what happens? We have 1 minus negative 1, that will be 2 over n, so that would give you 4 over n pi. Do you guys see that? Do you guys see what I did? So you have to let me know if you have questions or not, because if you don't, I wouldn't know if you want me to explain more.
Yeah, Professor, is it necessary to simplify it like further?
Yeah, because you don't want to add 0 coefficients. We want to avoid and simplify as much as we can. So that's why we want to conclude if n is odd, this is what happens. If n is even, this is what happens. Because this is something you can simplify. Sometimes you can't. So you will leave it as it is. But for this one, it actually simplifies to just 4 over n pi. So we would go further and use that as the coefficient for bn. Okay? So now that we have bn, so we found bn to be 4 over n pi when n is odd. So now our Fourier series, sine series, is going to be the sum starting at n equals 1 to infinity, bn sine of n pi x over L. Substituting our unknown variables, we have thus f of x is equal to the sum n equals 1 to infinity, but specifically n is odd, so you can write it like this, bn, which is 4 over n pi sine of nx, because L is pi, so that simplifies. So this is one way to express the Fourier representation of this. Or if you only use the rule for odd numbers, how do we express odd numbers? So odd numbers, we can express it as 2n minus 1, right? And even numbers, we express them as 2 times n, because any number times 2 will always give you an even number. And then 2n minus 1 will always give you an odd number. So if you want to use the rule, or you can say f of x is equal to the sum n equals 1 to infinity, 4 over n, well, n will be replaced with 2n minus 1 pi times sine of 2n minus 1 x. So this would be another way to express the Fourier sine series. Any of these are fine, right? Any questions on part A of this question? Greg, does this make sense?
So far, yeah. Just trying to catch up with the writing.
Okay, all right. Sadia, does this make sense?
Yes.
Okay. All right, now let's connect this with the heat equation, right? So if you go back to the question, we have part B to the same problem. It's just using part A because we know for the for the heat equation, we have, this is the scenario. So you have a heat equation, U sub T is equal to 64 UXX. So you should remember this 64 is your alpha square, right? Because we wrote down the heat equation this way. U sub T is equal to alpha square UXX. That's the general, or you can call it the standard way of writing it. And then we have boundary conditions, right? At the two ends when L is equal to 0, when X is equal to 0 and when X is equal to L, which is the length of the rod, we have a boundary condition and we always force them to be 0. It's just an ideal scenario. And in this case, that's true, it's 0. So this is the boundary condition. And then we have our initial condition, which happens to be the function from part A. So that's why when you set this up, the solution of the heat equation, that same coefficient Bn is the same Bn from the Fourier sine series. So that's why we use part A to fill in for part B. I hope that makes sense. So the only unknowns we have is L, which we know from part A, same as part B, pi, and we have to figure out what is alpha square. So from this question, alpha square is 64. And then we already know Bn, that's from, again, part A. So we just fill everything into our solution. So for part B, we know up to the boundary condition, the solution is Uxt is equal to the sum n from 1 to infinity, Bn, the same Bn from part A, times sine of, I think I wrote exponential before, e to the negative alpha square, n square, pi square, L square times T. Everything's square, right? So you can put everything together and then square it times T times sine of n pi x over L. That's the solution up to the boundary conditions. Now, once you apply the boundary conditions, this is the solution. Now, when you apply the initial condition, you have Bn, which equals to the Bn from previous part. So all we have to do is fill in what is this, and what is that. So these are the unknown you're gonna fill in from part A. So Bn, we computed, that happens to be 4 over 2n minus 1 pi. That's Bn. You can use this, or you can say 4 over 4 times 4 over n pi, where n will run all the odd numbers. But I'm going to use this one for simplifying. And then we know L, that's pi. And we know alpha squared, that's also given in the equation, that's 64. So we're just going to plug all of these in the right place. And that would give us the solution to the heat equation. Really, the second part doesn't require any work other than processing through what's going on, okay? Does this make sense, guys?
Yes.
Okay, so let's plug these in. So our solution to the heat equation, it's use U of xt is equal to the sum n equals 1 to infinity Bn, which is 4 over 2n minus 1 times pi times e to the negative alpha square, that's 64, n square, pi square. Well, n is odd, right? So we have to put the rule for odd numbers. 2n minus 1 square. and then pi square over L square, L is pi square, times t, and then sine of n pi x over L is pi. So that's the setup. Now just simplify this out. You know, pi square will cancel out, pi will cancel out from there, and all of this will just clear up to the sum from n equals 1 to infinity, 4 over 2n minus 1 pi e to the, let's see, okay, so we have negative 64, 2n minus 1 squared times t, sine of n times x. So that's our solution to the heat equation. Ooh, okay. Sorry, it looks weird, but that's the solution to this. Okay, so any questions on this problem?
Why didn't you replace the n in sine nx with the 2n minus 1?
Oh, because I forgot, sorry. Thank you. Good catch, good catch. Oops, right. Thanks a lot. So n is everywhere odd, so it'll be 2n minus 1 times pi will cancel out, so it's just x. So it'll be 2n minus 1 times x. Thank you. Now it's complete. Sorry for that typo and mistake at the same time. All right, so there you go, another example on Fourier series and heat equation.
Professor.
Yep.
Let's say you were given 6ut is equal to uxx. So what will be the alpha squared in that case?
So you said, what if you're given 6ut equals uxx?
Yes.
So you would move the 6 to the other side, so you'll have u sub t is equal to 1 over 6 uxx. So your alpha square is going to be 1 over 6.
Okay, got it.
So you always want to write it in u sub t equals alpha square. So alpha square has to go with u sub xx. All right, so any other questions? Or any questions in general? Anything you guys want to go over? This is your time, so use it wisely.
Professor, can we cover this one problem from the last exam?
Okay. Yeah. So I have to pull up the exam, so just give me a second. So can you tell me which problem?
Yeah, it was the particular solution one. Y prime, I mean, y double prime plus 6y prime plus 9y is equal to t to the negative 2 times e to the negative 3t.
Okay.
I just couldn't find the particular solution for some reason.
Okay.
Same here. That one got me.
Oh yeah. All right. So you said y double prime plus 6y prime plus 9y, right? Was that the one?
I'm sorry, I just lost the page. Okay, yeah. So it's y double prime plus 6y prime plus 9y prime. Yeah.
That one. Okay, so let's look at this one. So this is from exam 2, the one you just had. Okay. So, well, which method can we apply for this question?
Variation of parameters.
Right away, you have to be able to tell which method is applicable. So because of this function right there, it's not a polynomial. We straight run to variation of parameters. So let's do it. So first you want to compute the homogeneous solution. So we have y double prime plus 6y prime plus 9y equals to 0. So then we can write out its characteristic polynomial. That would be r squared plus 6r plus 9 equals to 0. And then we can factor this, right? Looks like this would do the job. R plus 3 all squared. So r is equal to -3, and it's repeated. Okay, sorry, that's so messy. Okay, well, we know how the solution looks like. So we have C1 e to the -3t plus C2t e to the -3t. Because it's repeated, so you multiply by t for the second function. So now we can label this is y1, and let's label this y2. What's the second thing you want to find for the variation of parameters method?
The Wronskian.
Okay, so the Wronskian of y1 and y2, it's going to be, so y1, that's e to the -3t, y2 is t e to the -3t. And then the second row, you're going to put down their derivatives. So e to the -3t, you differentiate, you have -3 e to the -3t. And the next one, product rule. So we have e to the -3t minus 3 t e to the -3t. So just double check my work. I hope I'm doing it right.
You're doing it right.
Okay, good, thanks. Always double check. Now we just kind of multiply them using the rule we have. So e to the -3t times e to the -3t, well, you add up their powers, right? So you get e to the 0, which is 1. And then the second one is minus 3t, and then minus plus, we have
Wait,
3.
No.
Hold on.
Negative.
What? What happened?
You said e to the -3t times e to the -3t, right?
Yeah, you add them up. Oh, sorry.
But that should be e to the -6t.
Sorry, guys. Yep. All right, I think my brain just froze. Okay, e to the -6t. Ooh, big mistake. All right, now the second one, we have -3t e to the -3t. No, hold on, sorry. Ugh. 6t. That was good, right? Okay.
Yes.
And now we do plus 3t e to the -6t. Oh, that's nice. Okay, so these cancel out. So our Wronskian is just e to the -6t. Oh, that's nice. Okay, now we have to figure out what is u and what is v, because the general solution would be u times y1 plus v times y2. That was the formula we wrote down. So u is equal to the negative integral of g times y2 over the Wronskian dt. So that's negative the integral of g. G is the function we have here. So this is g of t. So that's t to the -2 and e to the -3t. So t to the -2, e to the -3t times y2. Y2, we labeled it to be t e to the -3t all over the Wronskian, which is e to the -6t. And now you just simplify this, and what do we have? So all the exponentials will cancel out. We're left with only t to the -1 dt, right?
Yes.
Okay, and then this is the famous ln, right? Never forget the ln. Plus c1, so that's u. So we successfully found u. And now let's look for v. V is the integral of g times y1 over the Wronskian dt. And so g is again t to the -2, e to the -3t times y1. That's e to the -3t over the Wronskian e to the -6t dt. Again, the exponentials cancels out. We have we have t to the -2 dt. And if you integrate this, this is just -1 over t plus c2. Okay, so again, double checking my work. Yeah, looks good. Okay, now is the part you write out your general solution, and then from there we can pick up which one is homogeneous, which one is particular. So we know our general solution. It's going to be y equals u times y1 plus v times y2. So plugging these functions in accordingly, we have, so negative ln of absolute value of t plus c1, y1 was e to the negative 3t, plus v, that's going to be negative 1 over t, plus c2, y2, that's t times e to the negative 3t. And now if you distribute, you have y equals, so the first one, so let's write down the homogeneous one, which are the ones with c1 and c2. So we have c1 e to the negative 3t plus c2t e to the negative 3t. So that's coming from, sorry, that's coming from this one and this one. And the rest we just rewrite. So we have negative ln of t e to the negative 3t. And the last one we have negative e to the negative 3t because t over t is just 1. Now, if you look at it carefully, this solution and this solution, they're exactly the same one, right? They're just multiplied by different constant. First one has c1, second one you can think of negative 1. We can just put them together and just call it another constant times e to the negative 3t. So if you put those together, your final solution is just c1. So I'm keeping c1 instead of another constant, but you can change it to a d or whatever you like. I'll keep c1 plus c2 t e to the negative 3t minus ln of t e to the negative 3t. So here's your y sub h, and here is your yp. So any questions on that?
Professor.
Yeah.
Would you mark it wrong if I left it as like negative e, like e to the negative 3t at the end?
Oh, so you didn't put them together?
No.
Oh, I'll take a point off.
Oh no.
Yeah, just one. Not much, just 1 point. So any questions on that? Does it make sense?
Yeah, I just forgot about that method. I
Oh,
barely have to come back to it and rethink
okay.
it.
All right, well, now you know, right? So let's do better on the final. But you guys are doing well, so I wouldn't really worry for any of you. So just keep doing well, okay? Just keep working hard. You have 3 more days until the 23rd, and then do whatever you have to do. But until the 23rd, just keep studying, keep working hard. All right, so any other question you guys would like to go over? Should we just look at a final?
Professor.
Yeah.
Could you go over let me see, the heat equation from like spring 2017?
Okay.
That was question number 4.
Yeah. Okay, so let me just pull that up on my computer. You said that was number 4?
Yes, from spring 2017.
Found it. Oh, no. So I only got half of it. So just give me another second. Okay. So here's the question from spring 2017. So do you want us to do the entire part?
Just do the part B. I think I get the part A thing.
Okay, so what did she get for part A? So we need to use A for B. That's why I'm asking.
I got f of x is equal to summation from 1 to infinity 2 over n sine of nx. Yeah.
All right. So this is your Bn, right? Okay.
Yes.
So that's what we're going to use for the second part. So for part B, all you have to do is just fill in the missing variable.
Professor,
Yeah.
I got the same thing, but with a negative 1 to the n.
Negative
part A.
1 to the n. So your Bn was negative
was
1 to the n, like that?
with the 2 over n. Yeah, the only thing. No, it's the same thing that she had, but multiplied by negative 1 to the n.
Okay, so let's work it out. So
Yeah.
let's check, right? It doesn't hurt.
I had negative 1 to the n 2 times 2 over n,
Oh.
and then sine x.
So you had negative 1 to the n times 2 over n.
Yeah.
Okay, all right, so let's check. So let's hold on to part B. So we want to compute again the sine series. So that means you're extending it as an odd function, and then you can draw the picture, but we're going to avoid the picture for now. So here's the interval 0 to L. So L is pi, right? So we can determine that from the question. And it's the same L for the second part because there's the interval from 0 to pi, 0 to L. So because it's an odd function, that's how we're going to extend it as. We know A0 is going to be 0 and AN is going to be 0. So all of these coefficients are 0. Now BN, it's going to be, again, because you're doing an odd function times sine, product of two odd functions is even, so I can do 2 over L, integrate from 0 to L, f of x times sine of n pi x over L. So you can always write that down. Now L is pi, so we have 2 over pi, integrate from 0 to pi. F of x is pi minus x times sine of n times x, cx. Okay, so how do we integrate this? We're going to
Integration by parts.
by parts, right? So we're going to use the shortcut to by parts. So we pick a column for the derivative, and then we pick a column for integration. So I'm going to differentiate pi minus x, and we'll integrate sine of n times x. So differentiate pi minus x, that's negative 1, and then 0. Now integrate sine of nx, that's negative cosine of nx over n. And then integrate again, you get negative sine of n times x over n squared. So just double check. Yeah, that's right. So now we cross them this way, and then we multiply them with plus and minus sign. Okay. Okay. So now what do we have? We have 2 over pi times all of that. So we have pi minus x times, well, negative, so there's a negative, and then cosine of nx over n, taking it from 0 to pi. And then the second one, we have negative 1 times negative, negative, so we get negative. 1 over n squared times sine of n times x, going from 0 to pi. So that's what we have here. And then now let's plug in the upper limit for the first term. So we have 2 over pi in the front. If I plug in pi, it'll go to 0, right? Because pi minus pi is going to 0. If you plug in the bottom limit, you have minus minus, so that's plus pi over n. And then cosine of 0, that's going to be 1. Minus, now if I plug in pi for the second term, sine will go to 0. If I plug in the bottom limit, that will also be 0. Oh, how nice. Yay. Okay, so now if I just clear this up, this is nothing other than 2 over n, because the pi's will cancel out. So Bn is 2 over n. That's nice. Now we write out our Fourier representation of this. So our Fourier sine series, right, FSS, that's going to be f of x is equal to the sum starting at n equals 1 to infinity, Bn, which is 2 over n, sine of n pi x over L. Pi will cancel because L is pi. So that will be the Fourier sine series for this function. So let's see which one do we have. So this looks correct. Any questions on this part? Does it make sense, guys?
Yes.
Okay, that's a good yes. All right, now part B. Well, for part B, we need to know. So what do we need to know? So it's already in the form that we want, right? Ut is equal to alpha squared uxx. So what is alpha squared? That's going to
9.
be 9, good. And then we know L is pi, right? It's the same L from part A. Or if you forget, you can also look at here. This is the same L. Or you can look at here. It's the same L. 0 is the one side of the rod. Length of the rod is pi. And then initial condition, it's the same function from the previous part. So again, it's the same Bn that we're going to be using for this solution. So let's plug these in. So part B, so we're going to plug in alpha square, which is 9. We're plugging in L, which is pi. Bn, that's going to be 2 over n. So our solution to the heat equation is simply u of xt, the sum from n equals 1 to infinity Bn, which is 2 over n times e to the negative alpha square, that's 9, n square, pi square, L square, L is pi, times t times sine of n pi x over L. L is pi. So plugging those in and simplify, we have our solution. Use of xt is the sum from n equals 1 to infinity, 2 over n, e to the, so the pi squares will cancel out. There's just negative 9n squared t sine of n times x. So that would be the solution. So you already did all the work for part A. Part B is just set them up correctly. That's pretty much it. Because both functions will always match. If they don't match, then you have to do extra work, go for solving for Bn, which we know how to do just by setting t equals to 0. You have your initial conditions. All right, so that's the question from spring 2017. This was spring 2017. All right. So any other questions or any questions on this?
Also, from the same final, can we do 7 part B?
Okay, 7 part B. Okay, so 7 part B. So here's question 7 from the same final. So we kind of need part A for part B again, right? Because, so what was the answer to part A?
I got C1 e to the t plus C2 t e to the t plus C3 e to the t cosine of radical 3 times t plus C4 e to the negative t sine of radical 3 times t.
Okay, so that was part A, which we call it,
Professor,
yeah,
it's e to the negative t for C3 and C4.
okay. All right, so negative, negative, and this is kind of like the solution to part A. And then, well, that was the solution to the homogeneous part. So any questions on that part? So this question was nice, right? He's so generous. He gave you guys, hey, look at that. It's like awesome, right? You don't have to think about it, how to factor this. Whew. Okay, so that's covered. Now, for the second part, you just want to determine what will be the form of the particular solution so that they're independent from part A. So first one, let's check this out. So we have an exponential. Let's call this yp1. And then we have, so this will give us another form. Let's call this yp2. And then, oh. So it looks like they both have same argument, the second and the third function. So I'm just gonna call that entire piece to be yp2. So the reason I'm doing that is because they have the same argument. Oh no, hold on, sorry. Let me backtrack.
No, one is negative t and then one is positive.
Exactly, so let's keep it that way. I thought they had same exponential as well. So this would be yp2 because the exponentials are different, so no way. And then yp3, and then the constant will get another form. Okay, cool. And then the particular solution will be sum of all of these little particular solutions. So let's figure out what's yp1. So we have a constant times exponential. So we need a constant times the same exponential. And now try to match up. Does this overlap with part A? Yeah, right? This piece. And then this piece, if you multiply it by t. So how do we modify this?
You have to multiply by t squared.
Right, so if I do t squared, it's fixed. Moving on to the next one, yp2, we want a linear, right? T is linear, the exponential e to the t, and then cosine of the argument, square root of 3t, and sine of square root of 3t. So we want a linear function, so let's call it bt plus c times the exponential e to the t cosine of square root of 3t plus another linear function. So a, b, c, d, t plus e to the negative, no, not negative, t, and then sine of square root of 3t. Okay, so that's a possible form. Now let's check. Does any of these overlap with my homogeneous solution?
No.
No, right? They're all fine because the exponential term on the one we have in the homogeneous is negative t. So perfectly fine, no need to modify. Let's go to the next one. So we have exponential of negative t and then sine of square root of 3t. So we need sine and cosine with that. So yp3 is going to be, so we need, so I got up to e, f e to the negative t sine of square root of 3t plus what after f? G e to the negative t cosine of square root of 3t. Okay, now let's look at it. Do we need to modify this one? Yeah, right?
Yes.
Yeah, so how do we modify this?
Multiply by t.
Right, so we take this and multiply by t because then it will be independent from the homogeneous solution. And now the last one is just a constant. So we need yp4, which would just be a constant h. Looks like use almost all the alphabets. So, okay, h. Does it overlap? No. So we have all of it. So if you just put all of them together, your particular solution is yp1 plus yp2 plus yp3 plus yp4, and then you just write them all out. Here you would distribute this function, and then the rest you just write them out. So I think you can fill that in, right?
Yes.
Okay. All right.
I messed up on the YP2. I was like confused. Should I break down t e to the t or the cosine of square root of 3t? I was confused on that part.
Oh,
Because
okay.
they're both like, you could break down both, but which one like comes first or which one second? Like I was confused on that.
Okay. So does it make sense now?
Yeah, it does.
Okay, that's great. All right. So yeah, any other questions, guys?
I mean, go back to the last exam that we had.
Okay.
This question is it was 1 minus x squared y double prime plus 2x y prime plus y is equal to 0.
Hold on. Exam, right? So, okay, which question was it?
It was 1 minus x squared y double prime plus 2x y prime plus y is equal to 0.
Okay, this one.
Yeah, that'll be. Yeah.
So I'm just gonna crop this to one note. So for me, it's label number 4, but of course for you, it's not number 4. Okay. All right, so we want to find recurrence relation for this. So I didn't have you write out the solution, but maybe we can write out the solution at the end, right? We'll take it one extra step. Why not? So we're assuming the solution form is the sum starting from n equals 0 to infinity a n x to the n. So you compute its first and second derivative, plug everything in. So y prime is going to be the sum. Again, I'm going to ignore indexing because you saw how we don't really need it for these type of problem for this course. So not sure if you're gonna need it for other courses. So the first derivative, it's going to be n times a n x to the n minus 1. The second derivative is going to be the sum n times n minus 1 a n x to the n minus 2. Now I'm going to distribute the y prime for the first term because it's much simpler that way. So we're using 1 times y double prime minus x squared y double prime plus 2x y prime plus y equals to 0. Now let's substitute our summation into this. We have the sum n times n minus 1 a n x to the n minus 2. For the second one, I'm just going to show less steps. So I'm going to push this inside the second derivative and it will simplify. So we have the sum n times n minus 1 a n x to the minus 2, and the 2 will cancel out. So you'll just have x to the n. Let me know if you have questions on that. And then for the third one, I'm going to push x inside the first derivative to simplify that power. So you'll have 2 times the sum n times a n x to the n, because minus 1 and x will cancel out. Plus y, that's just the sum a n x to the n equals to 0. So this is pretty nice, right? You're welcome. It's really nice summation that I gave you. So all of these can use the same substitution, k equals n. And just for the first one, we can do k equals n minus 2, which means n is k plus 2. So that's pretty cool. Well, now we can rewrite everything in terms of this new k variable, and every x will now have the power x to the k, and I can pull that out and rewrite all of its coefficients. So for the first one, we're going to have, so n is going to be k plus 2, and then n minus 1 will be k plus 1, a sub k plus 2, x to the k, factoring it out, minus k times k minus 1, a sub k, plus 2 times k, a sub k, plus a sub k, everything times x to the k equals to 0. So I skipped a lot of steps, so let me know if you have questions. Now, we want the coefficient of x squared, x to the k to be 0, so we set this equals to 0. So that would give us our recurrence relation, and we solve for the highest subscript, which will be this piece right here. So if I go ahead and solve for that, I would have a sub k plus 2 is equal to, so move other terms to the right side, we have k times k minus 1, a sub k minus 2k, a sub k, and then minus a sub k, everything over k plus 2 and k plus 1. And the top, you want to simplify it as much as you can because none of this will match with the answer I gave you. So we got to do more work. So pull out a sub k. So you're left with k squared minus k, and I'm distributing at the same time for the first term. And then I have minus 2k minus 1, everything over k plus 2 and k plus 1. So all of this would simplify to simply k squared minus 3k minus 1 a sub k over k plus 2 and k plus 1. And that's the simplest we can get. So if you were to look at one of these choices, oh, there you go. Aha. So that would be the right choice.
I got the same answer, right? But then they marked it wrong.
Oh, because I had a typo on the solution and then I fixed it. So you got credit if you picked 2.
Oh, okay.
Yeah, so yeah, double check your exam if you want to. You got credit for this if that was the answer you chose. Now, what if we want to take this question further and just write out, like, let's say 3 non-zero terms, okay? So why don't we go ahead and compute a few more coefficients, okay? So we know A0 and A1, they're the initial conditions, which I didn't give you in this question, but let's for now pretend they're just themselves. Now let's find A sub 2. So I can find A sub 2 by k equals to 0, right? So we're just doing a little bit more work on this question. So if I let k equal 0, I get A sub 2. So we have negative 1 a sub 0 over 2. That's pretty nice, right? Let's go for one more. K equals 1, you have a sub 3. So we will have 1 squared, that's 1, minus 3 minus 1 times a sub 1 over 3 times 2. So that would just give us negative, what's the number? Negative 1 over 2 a sub 1, right? Yeah. So we have 4 non-zero terms. Let's see how the solution would look like. So the solution to this problem, if I asked you, right? But you might have it on the final, who knows, right? Why not? So we have the sum an x to the n. So let's write out a few terms. A0 plus a1 x plus a2 x squared plus a3 x cubed, so on. So plugging in these coefficients, we have our solution a0 plus a1 x plus a2. Well, a2 happens to be negative 1/2 a0 x squared. And then a3 is also negative. So how did they both happen to be 1/2? Oh, did I do something wrong? I didn't. Okay, they just happen to be that. Okay, who cares? X cubed plus so on. And then you want to write them as a 2 independent solutions. So I'll write the terms with a0 and a1. So we have a0, 1 minus 1/2 x squared plus dot 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 plus a1 x, and then the second term is minus 1/2 x cubed and so on. So that would be 2 independent infinite solutions of this, right? Another way to represent the solution. And you can think of your A0 and A1 as C1 and C2. So any questions on this? Well, how do you guys feel?
It makes sense. I thought I did something wrong because the test marked it wrong.
Okay. No, you didn't do anything wrong. It was me. So good job. You did it right. Okay, so any other question you guys want to go over?
Professor, could we look at one of the problems from the 2011 final?
Mm-hmm. Okay, so let me just pull that up. Okay, so which problem do you want to see?
Number 9.
Number 9. All right, so I'm just gonna copy that to OneNote. Okay, so that's number 9 from, this is the one, right?
Mm-hmm. Yep, that's it.
Okay.
Would
All
you
right.
mind just walking through getting the roots real quick?
Okay. So, so you don't want the full solution, you just want the roots?
No, because I was able, because I also looked at the solutions, and I was actually quite close to the full recursion formula. But it was when I got to the roots part, I noticed that it doesn't begin with 3x squared y double prime. So I was kind of curious how that changes things.
So what do you want to do? You want to write this in the standard form of an Euler equation. So we would multiply the entire equation by x.
Oh, right.
And then everything will fall in. Yeah.
Okay.
So because it doesn't have the form we want to force it so that it has the form we want. So you would multiply, so we have 3xy double prime plus 2y plus x plus 5y equals to 0. So we want to make this into an Euler equation. So, sorry, multiply by x. That will give us x squared that we want for the second derivative. So if we do that, we have now 3x squared y double prime plus 2xy plus x squared and then y and then 5xy, right? So I distributed and I multiplied x at the same time for the last term. Well, now you can kind of pick up which would give you the alpha, beta, and gamma, right?
Right. I mean, when because I didn't do that, but I still was able to determine that it was finite through the limit process.
All right, so if you take the limit, it will give it to you as well.
Right.
So what did you get for, so what happens to beta?
Beta becomes, which one? Beta becomes 2/3 and gamma goes to 0.
Yep, absolutely. And then there you go, you have it.
Actually, if there's no objections from anyone else, would you mind going through this full problem?
Yeah, let's go. So let's finish this problem. So we want to, so that's one way to do it, right? But multiplying by x, and then you can identify your coefficients. But if you just take the equation that's given to us and compute its limits, we can still get our beta and gamma, right? So we take the limits as x approaches x naught. We're given x naught is 0, so x approaches 0, of x minus x naught, which is 0, times So this is P, this is Q, this is R. That's the notation we used. So we do 2 over 3x, and then take the limit, and this would give us beta. So what is this limit? There'll be 2 over 3, right? Because the x's will cancel out. So these guys cancel out. And then for gamma, we take the limit as x goes to 0 of x squared times the loss function over p of x, so that's x plus 5 over 3x. And then if you simplify this, so this would give us gamma. What is this limit? So this will be 0, right? Because if you simplify, only x will cancel out with one of them, and then you're left with x times x plus 5. As you plug in 0 for x, you'll go to 0. So we have our coefficients. So the corresponding Euler equation, so the corresponding Euler equation, it's going to be y double prime plus beta x y prime plus gamma of y equals to 0. That's what we wrote down. And these are the coefficients we get from the limits. So we have y double prime plus 2/3, 2/3, right? Yeah, 2/3. X y prime plus 0 y, so that disappears, equals to 0. And then from here we can write down the initial equation, right? Which would be r times r minus 1 plus 2/3 r equals to 0. And then of course we want to avoid the fractions. We multiply both sides by 3. So that would give us 3r times r minus 1 plus 2r equals to 0. And we look for its root. So we have 3r squared minus 3r plus 2, that's just minus r, equals to 0. So then we factor out r, we have 3r minus 1 equals to 0. Hence, we have r is equal to 0 and r is equal to 1/3. So these are the roots. Okay, so we have, did you get the same roots, Greg?
I wasn't able to make it that far. Yeah, this was the process that I hadn't forgotten about.
Okay, but does it make sense now?
It
Yeah,
does.
the roots are correct.
Okay. All right, so that looks good. Now what else do we want to do? So we want to show it's a regular singular point. Okay, we got it. Now recursion formula. Okay, so we have to assume the power series solution centering at x naught, and then blah, 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 right? And we are going to write out the solution using larger root. So let's continue. And we're also going to use a0 as 1. So that's also given. Okay, so let's compute the recurrence formula. So if we have the roots, let's hold on to them until the very end. When we write out the solution, we use the bigger r, which is 1/3. So we're going to assume that the solution form is going to be the sum an x to the n plus r. And then we compute its first and second derivative. So we have y prime, which is the sum from an x to the, oh, sorry, forgetting my stuff. Bring down the power, n plus r, an x to the n plus r minus 1. And then the second derivative, that's going to be the sum n plus r times n plus r minus 1, an x to the n plus r minus 2. All right, so you gotta be extra careful on that, right? Okay, now is the fun part. Plug everything in. So now you have options. You can either plug it into the original equation that's given to you, or you can plug it into this one that we just modified by multiplying everywhere by x. So it doesn't matter which one you use, it should give you the same formula. But I'm gonna go ahead, plug it into this form that I found by multiplying by x, because the powers will just become really nice when you use this one. And you'll see why later on. So let's use this form. So I'm just gonna copy and paste. That way I can save some time. So let's copy this. All right. So we plug in our summation into this form. And now let's erase the box. Okay. So what happened as you plug these in? All right, so let me just get the right color. So we have, what do we have? We have 3 times, so I'm gonna plug in, so as I push in x squared into the second derivative, we have the sum from n plus r times n plus r minus 1 an x to the, so the minus 2 and the 2 will cancel out, it's just n plus r. That's nice. And then for the second one, we have, what do we have? We have 2 times the sum. Oh, I think I made a mistake. Did I? Hold on.
Yeah, it should be
Yeah.
y prime.
Y prime, yep. And then the last 2's are y. Okay, good. All right, so it looks so odd. There you go. Okay, so now, oh no, sorry, not that one. It should be, where is it? It should be this one right here. Okay, well, now it makes sense. So we have 2 times n plus r times an x to the n plus r, because minus 1 and x will cancel out. And in the last 2 terms, we have the sum from an x to the n plus r plus 2. And then the last one, we will have the sum from, so 5 times the sum an x to the n plus r plus 1, all of it equal to 0. So let me know if you guys have any questions so far. Okay, so now we want to match up the powers. So let's see. So the first 2 looks fine, right? So these you can use k is equal to n because you want the power k plus r. And then the last 2, what can we do with those?
You have to do k equals n plus 2, and then for the second one, you have to do k is equal to n plus 1.
Okay, so then this would be n equals k minus 2, and this would be n equals k minus 1. Okay, fixed. All right, so now it's much nicer. So I'm just gonna hold on to the first 2 because all I have to do is replace k with n, so I don't have to really rewrite them. But the last 2, I'm just gonna rewrite them. So I'm kind of skipping steps. And then, so if I rewrite them using the k variable, we have a sub n, that's gonna be k minus 2 x to the k plus r. And then for the last one, we have 5 times the sum a sub k minus 1 x to the power k plus r. Okay, so now that their powers are matching, I'm going to write down all the coefficients and then multiply by x to the k plus r. That's the next step. So now we have the following. We have the sum. So the first 2 summation, replacing all n with k, we have 3 k plus r minus 1, a sub k, x to the k plus r, factor it out, plus 2 times k plus r, a sub k, x to the k, oh, I'm factoring k, x to the k plus r, so ignore that. And the last 2, I have a sub k minus 2 plus 5, a sub k minus 1, everything times x to the k plus r equal to 0. almost done. So now is the fun part where you just set the coefficient equal to 0 and solve for the highest subscript. In this case, it's going to be this piece right here. All right, so I'm going to set this equal to 0 and solve for a sub k minus, sorry, a sub k. So we have a sub k, which is to subtract a sub k minus 2 minus 5, a sub k minus 1, and divide it by 3, k plus r minus 1, plus 2 times k plus r. So that's the recurrence relation in general. Now we want to find the recurrence corresponding to the larger root, right? So compute the recurrence formula for the coefficients of the Fourier series center at x not equal 0, which is associated with the larger root of the initial equation. All right, so larger root, which was 1/3. That's what we computed, right? So if I plug that in, I have a sub k, which is negative a sub k minus 2 minus 5 a sub k minus 1 all over, we have 3 times k plus 1/3, and then k plus 1/3 minus 1 plus 2 times k plus 1/3. And we can actually simplify this more. So let's do that.
Professor, your voice is cutting.
Yeah, okay. All right, hello, hello. Can you guys hear me? Is this
Yes.
better? Okay, all right, thank you. So I plugged in r equals 1/3, and I'm just gonna simplify this more. So we have negative a sub k minus 2 minus 5 a sub k minus 1 over, so I'm just gonna distribute the 3 and simplify. Or maybe not. Should we distribute? What should we do?
Okay, so the bottom should be 3k squared plus k minus 4/3.
Did you simplify all of that?
Yeah.
Okay, so tell me one more time. Sadia, one more time.
Hello?
Yeah, tell me one more
It's
time.
3k squared plus k minus 4/3. Yeah.
All right, so I will take that as an answer. but you see, rest of it is just algebra, so I'm sure you guys can figure that out. At this level, you should do it. You can do it. So there's no need for me to show you how to simplify fractions. We all master that. That's why we're here. All right, so there you go. You have your recurrence relation. And of course, you can play around with this, factor out the 3 again, and then rewrite stuff. But I wouldn't do that. But yeah. So we have our recurrence relation, and the next part is to so you want to compute A1 and A2 when A0 is 1. Okay, so we just need to compute A1 and A2 using A0 as 1. Okay, so we can do that. So we know A0 is 1. So what is A1? So if I let K equals to 1, that will give me A1, right? So A1 is going to be negative A sub negative 1 minus 5 A sub 0 over, so K is 1, so that's 3 plus 1 minus 4/3. Now, what did we say about the negative subscript?
Professor. Hello?
Yeah.
Just, can you take out the minus 4/3? It doesn't belong there.
Oh, it doesn't? Okay. All right, so
No.
you double checked. Thank you. So, all right, so Sadia changed her mind and she said this is it. So, right, so. Let's confirm this is right. Okay, so so what do you guys have for A1? So I just have to fix the bottom part, right? So what did we say about negative subscript?
They go to 0.
Right, so this is 0. So what we have is, and A0 is 1, so I can plug this in. So we have negative 5 times 1, that's negative 5 over 4. So that would be the coefficient, A1. Now let's find A2. When k is equal to 2, we can find A2. So we have negative A sub 0 minus 5 A sub 1 over 3 times 2 squared plus 2. So now plugging in A0 and A1, so we're going to have to do more calculation on this. Did anyone computed this? So A0 is 1, and A1 we just computed, that's negative 5 over 4 over what? 4 times 3, that's 12, plus 2, that's 14. Okay, not bad. Just have to work with fractions. So we have 1 minus plus 25 over 4 over 14. So whatever that number is, that's A2. You guys can figure that out, right? Common denominators, add them up, and then divide it by 14. Okay, so there you go. This is the complete solution to this problem. Again, I didn't add the numbers up. I know you can do that, so that's for you to figure out. Okay, so any questions on this? Are we good so far?
Yep.
Okay, thank you, Simon. All right, so yeah, so any other questions? Any other questions in general?
Professor, I'm having a little bit of trouble with, I'm sorry to go back to the Fourier series, but I'm having trouble with like some of the odd and even functions because sometimes it mixes me up, so I don't really use a shortcut. But when I work it out from negative pi to pi or whatever, I don't get the same answer as you.
So if you don't get the same answer as me, then I would say just double check the integration and carefully double check your upper limits and bottom limits.
So like this question right here, right?
Yeah.
Said that for 1 times sine, it would give you an even function, but sine is just sine is an odd function, so I don't understand how you're doubling you're doubling like 2 over pi.
Oh, so the reason I doubled, because if you look at the function 1, it's just a constant function, right? But we extended it as an odd function. So the extension we did for 1 period, which was right here, we extended it as an odd function. So that's why we have f of x is odd. And then sine itself is also an odd. So odd times an odd function is even. That's why for the next step, I doubled it.
Okay, I see it. Thank you.
But if I were to extend this as an even function, so the picture of an even extension will look like this. So we're at 1 from 0 to pi. If it's even, you just reflect it about the y-axis, right? So that would look like this. That would be an even extension. And then, of course, all of these will change. Everything will get modified. B0 will go to, I'm sorry, Bn will go to 0. A0 will survive. An will survive. So you'll have a completely different coefficients and completely different representation of this Fourier series.
Okay, so I see. So every time you do an odd extension, it's automatically going to be an odd function, and then you're going to multiply by sine, which is going to give you an even function to integrate, right?
Yep. So this would happen all the time if you're doing an odd extension.
All right, thank you. I got it.
No problem. All right. Any other questions, guys? Are you guys ready for the final?
I hope so.
Yeah.
Closer.
I'm sure you guys are ready. Just keep studying. And so we have another review session tomorrow. Again, same time, 5 to as long as you guys want. But I'm hoping to go for 7 p.m. And after that, I will probably be pretty tired. But if you guys wanted to call it a day for today, that's okay. If you want to do more example, that's also okay. So you guys decide for next few seconds.
Professor,
Yeah.
you're gonna upload the solutions for the both finals, right?
No, not for both. I only have spring 2017.
Okay.
The other one, I have it right here. I didn't do it. I was hoping to go over this with you guys during this session. So maybe you guys can work on it tonight, or, you know, whenever you have time, work on it. And then you can check it with me tomorrow, because I do want to go over at least one complete final with you guys. So I would say for tonight, work on this final. I'll put up the solutions for spring 2017. So if you did that one, you can check it. If you didn't, hold on to it. You can do it after tomorrow, because I wouldn't be writing solutions to spring 2019. That I want to do it in the review session. Since I already did the other one, it wouldn't make sense to do those questions. It's already written for you. So yeah, so let's work on this for tonight, and then I will take questions from spring 2019 tomorrow. And then if you want to work on any other questions, I can also do that tomorrow. What do you guys say?
Yeah, sounds good.
Okay. All right. So we'll end our session here for today then. I will see you guys tomorrow, same time.
Thank you, Professor. Yeah.
Thank you. Thank you.
Yep, no problem. I will see you all tomorrow. And keep studying hard, okay? You guys are doing great, so keep working hard. All right, so I will see you all tomorrow, and we'll continue with more reviews.